Hello and welcome. In this short video, I will demonstrate how to create a terminal interface for your Arduino robot projects. Firstly, you have to download the Arduino IDE from its website. It's very easy, just go to arduino.cc, software, and download the latest one. After you installed the Arduino IDE, just open it. Basically, that's all you need to do. You can start programming. In order to create a terminal interface, you will need two software packages. The first one is Shellminator, the second one is Commander-API. Shellminator is a VT100 enabled terminal interface which can communicate with PuTTY, TerraTerm or Minicom. Commander is a text-based command parser and it can be used to process text-based data. All of them are available at Arduino Library Manager. To install them, you need to open Sketch, Library Manager, and search for the two libraries. Once you found it, choose the latest version and select Install. The same for Commander. Basically, that's all you need to do. You can start programming. I would like to tell a few words about the Shellminator and the Commander projects and how to use their documentation for your future projects. So if you open the repository for those projects, you will see the documentation section. If you click on the link, it will go to a documentation which is generated by Doxygen, and it contains all of the features which the library has. For example, if you go to the classes and search for Shellminator, for example, Doxygen extracts all of the data types, all of the member functions, and it's usually a very easy way to see the full API of these libraries. Usually it also generates hierarchy graphs, so it's much easier to understand how and why it works. I tried to note out the dangerous parts of the code. If there's some external links, you can also interact with them. So please, if you have any problems or you don't understand something in this video tutorial, open the documentation and read it for that part. I hope it's clear and it will be understandable for anyone. I also like to mention out that these libraries are a bit memory hungry. So if you want to use them with an AVR, for example, the Atmega 328, which is used by the Arduino Uno platform and the Nano, it might have less RAM than you need. So these libraries often use relatively large buffers, I mean 30, 50, 100 bytes of memory to work, and it's relatively big memory usage in a platform which has only 2K bytes of memory like the Uno. But if you use it with ESP32 or ESP8266, it's a very good platform, or even with the Arduino Mega, which has much more memory than the Uno. So if you build a system which using these libraries, I think a good practice is to have at least 2 kilobytes of memory which is dedicated to the terminal interface. Also, if you find some problems with the documentation, it can be anything, a typo, misspell, something you doesn't like or you doesn't understand, please note it in the issue section. There are templates for it. I would really appreciate it, because as you can hear, my English is not the greatest. I'm working on it. But if you have some free time, please report that as a bug, and I will do my best to fix the documentation issues. Thank you. I made a small little project on a breadboard, which consists of an ESP32 base board, an LED and a servo. Let's imagine that's a very simple robot you want to make, and you want to control the servo, the LED and some wireless stuff in your project. Of course, if you want to make more complicated projects, you can use the knowledge from this video as well. Okay, so quickly I just created a sketch which demonstrates the basics, how to create a project with Shellminator. So we start with Shellminator because it demonstrates how to use the terminal interface and how to connect it to PuTTY. We have to start with there. So we have to include two header files. The first one is called shellminator.hpp, which contains Shellminator itself. The second one is shellminator.io.hpp, which contains all of the communication pipings to select the communication channel. So we have to create a Shellminator object. I will call it a shell, and I connect it to the serial object in this project. In the main loop, we have to create the serial communication itself with serial.begin at 115200 baud rate. We just print out program start and begin the shell with a username called demo. In the loop, we have to update the shell object to process all the new data which coming from PuTTY to the device. Let's try that. After uploading, we have to open a terminal to check if it's working. So we need a terminal emulator like PuTTY. PuTTY can be downloaded from putty.org and it's free. Just download and install it. After the installation, we need to open a serial port to connect to the panel. In my case, it's COM5 with this speed. Just to simplify things, save it in PuTTY to easily access it next time. So as we can see, it's working. We have the program start message and we have a terminal. So if we press the return key, we should see that the terminal is working. Type commands and it echoes back them. This terminal has history, so if you press the up and down keys, it works as well for the previous commands. You can edit the text what you typed in. It's very interactive. Let's start communicating with our peripherals. Start with the servo motor. We need ESP32servo.h library from the library manager to use the servo, and we define which pin we'll be using the servo. In my case, it's pin 33 or GPIO 33 on my ESP panel. We also have to create an object for the servo. Let's just call it servo. So as we can see, after the panel boots up, it prints out a lot of boot messages. I really don't like them if I use the terminal, so let's get rid of them. There's a command for it, which is shell.clear. It basically just jumps the cursor to program start message, and all of the data will be available if you scroll up, but if you open the terminal, you won't notice them. Basically, you want to put all of the initialization sequences into this area and print out the status of the initialization section. In my case, servo library doesn't have any feedback about successful or failed attempts, so we can just print out OK and hope for the best. Let's try out our modifications. So if you get this error, it's because you left PuTTY open. If you left PuTTY open, it uses the serial port for your board, and Arduino IDE can't open it. And if it can't open it, it can't upload the program to your board. So you have to close PuTTY every time when you want to update a new sketch. So the sketch is uploaded. Let's open PuTTY once again and see how it works. Okay, as we can see, the servo is initialized, the sequence is finished. Let's do that as well for our LED. So basically just define the pin of an LED, then initialize it with output and let the state 0, which means it doesn't lit. So basically we finished the peripheral init section. We could use the LED and the servo as we want, but to glue that to the terminal interface, we need a function which will be called every time you hit an return key in the terminal and tries to execute the command you typed in. So this function is called the execution function, and you have to pass the name of the function to the constructor of the shell object. Also, we have to create this function because it's just a declaration. So let's put it to the end of our file. And basically what this will do is just print out that it's called and it received the command. This command should be a command which you typed in to the terminal interface. So let's try this out. If we type something into the terminal like hello, as we can see, the execution function has called and it received a text which I typed in. So we can try it to anything. So it works, as we can see. So basically we have a terminal interface, but it can't parse the data which we type in. So we need some way to check if the typed command is valid and do something if it's correct. So let's modify the execution function. So basically with this modification, we just checks the received command if it's a LED on or a LED off, else print that it's not a command, and turn on the LED or turn off the LED depending on which command we typed in. Let's try this out. So if we type LED on, we should see that the LED is lit. We type LED off, it turns off. And if we type something else, it should print out this is not a command because it doesn't recognize it. So it works as we expected. I would like to show you a really nice feature of Shellminator, which is text formatting. So basically you can change the text format of the terminal with a simple command called set terminal character color. To see the full API of Shellminator, you can go to the GitHub repository and click to the documentation. It's a Doxygen generated documentation where you can find all of the available functions for Shellminator, like set terminal character color, and it's basically an interactive way to see the full API without browsing the source code. So let's do that. So we set a bold font with red color to print out the command which is not available. Then set back the text to regular format with white color. Let's see what does it does. So let's try that out. So hello is not available and it prints out with bold font and red color. In this way it looks way better in my opinion. So let's modify a bit the startup sequence and create a function called print OK. It basically just prints out a formatted green OK and use it instead of the regular one, like here. This way the code will be much shorter and the output looks way modern and professional, in my opinion. Let's try that out. So as we can see, it works. It looks much better, in my opinion. Of course, you can change the behavior, the format, and everything as you like. Just check out the documentation and you can see which colors are available and which modes are available for your text formatting. Of course, if you have more commands, you can create more else ifs for your commands, but it gets very confusing if you have more complex stuff in your execution function, and it will be very hard to read after the 14th or 15th command. So it is not the recommended way to do, but if you have a tiny project like an AVR project with a small amount of commands, it can be good as well. I would like to show a better way to organize your commands and make the code much simpler and faster. So here where Commander-API comes into place, let's include that. We have to create a Commander object that's called just Commander. We have to create a special array as well called API tree, which consists the data for every command in our project. So it has a name, it has a description, and a function pointer to a function which will be called when we type the specific command. So we have to create the functions as well. So once again, we need an array which consists the data for all of our commands. They have to have a name, a description, and a function to work. Right now they won't do anything, just make them to compile our project. In the initialization section, we have to initialize Commander as well. And let's just remove everything from the execution function for now. To call the specific function, we have to pass it from the Shellminator to Commander. It is very easy, just one line. So we basically just call the execute function from Commander and we pass the data we get from Shellminator to Commander. Also, we have to specify which peripheral we want to respond back. So as we can see, the initialization of Commander is finished. Terminal still works, but if we try our functions, we can see that it doesn't work as before. It's because we didn't implemented the behavior of the functions right now, so let's do that. It's very simple, just a digital write, and we turn on or off our LED pin according to the function. Let's try out. As we can see, it works as before, but the code itself is much shorter and simple. But it can be simplified a bit, and I will show you how to do that. So Commander and Shellminator are made to work well with each other. So if we use Shellminator with Commander as a command parser, we can pass the Commander object to Shellminator to use that for command execution. To do that, we have to modify the initialization section with one line and tell Shellminator to use Commander as a command parser. In this way, we doesn't need the execution function at all. So we can delete it. And the prototype as well. Also, we have to remove the execution function from the constructor. Let's try it out. As we can see, it works. And the code gets much shorter and simpler. So it's basically 95 lines, including comments. And we have a working terminal interface which is interactive. We can add our functions and commands to it, and it looks nice. So you can note that the commands are turned to green. Why is that? This is basically because if you use Shellminator and Commander together, we have some useful features like text highlighting and autocomplete, which works with the tab key. So if I type LE and press the tab, it tries to complete the text with an available function or command. So basically we have LED on and LED off, so it completes until it have a conflict like the N and the F key, so we have to fill it manually. But if it's an available command, it will be greened out, indicating that it's available for use. If it's white, it means that it's not recognized as an internal command, so you can't use it. I think it's time to talk about some really interesting features in the terminal interface. For example, the help function. So if we type help and press the return key, it will list all of the available commands for us. For example, we have LED on and LED off functions, but if we want some more information, we can use help-d, and it's basically the same, but it prints out the description information for all of our commands. If we know what command or we want to use, but we doesn't know how it works, we want to know some information about it, we can use the question mark after the command, and it will print out the information for us. By the way, this information is the text what we specified in the API tree. So for LED on function, we specify turn on the LED text and it will be displayed. So let's create a function to control our servo. This command will be called setServo. We write some useful information about it and we specify which function will be called when we use this command. So let's create that function too. Firstly, we create the prototype for this function. Then we create some basic logic for it. So we have to understand why is this response argument used in Shellminator and Commander. Basically, if you have a lot of channels where you can communicate, for example, a TCP socket, UART, I2C, everything you want to use, Shellminator will automatically pipe it to Commander, and Commander will pipe it for you. So you doesn't have to create a ton of function or overload it. It will be handled inside the libraries, but you have to use the response function to generate response texts with pointer arithmetics. It's very simple. Just follow the examples and you will get it soon. The other argument for our functions, which is always available, is args. Args is a character array, and if we specify some arguments, it will be passed through this variable. For example, if I type LED on, then some texts, this text will be passed through the argument variable to our function, and we can do everything we want with it. For example, we try to read a number out here and pass it to the servo-pos variable. Then we just print out the servo-pos variable to check if it's work. So let's burn it and see how it works. So let's try out. Also, we can use the tab key to autocomplete the command. then a space key, and specify some argument, number argument. As we can see, the argument is working, so we passed 123 as an argument to our command. It read out this argument, then it printed back. The problem with this implementation is that the argument can be anything, a string, a floating point number, so we have to make sure that the parsing done correctly. So let's create a variable called argument count, then store the return value to it. Basically, scanf-like functions return a number which represents how many arguments are passed correctly. So in this case, we try to pass one decimal number from the argument string, so it should return exactly 1. So if it's not exactly 1, something went wrong. Let's implement some logic with error handling. So basically, we just compare the argument count and see if it's not 1, because if it's the case, there's a problem. So we print out the problem, then we return, because we can't use a wrong argument. It could be catastrophic in our robot's life. Then we have to make sure that the typed value, if it's a number, is correct. It's always a good practice to check the boundaries of our numbers, because the servo can go from 0 to 180 degrees. So basically, this is the whole function for the servo communication. Let's try out before we pass it to the servo itself. Just make sure if it works correctly. If we try this command without an argument, we should see that it doesn't specify any argument, so it's a problem. Also, if we try it with some wrong arguments like text-based, it also gives an error and doesn't do anything, so it protects our peripheral or some motor or something which can go wrong. If we use it like intended, like 90 degree, it prints out the number without a problem, so it's like it's working fine. Also, if we use the question mark, it specifies which kind of arguments can be used. So the description for the commands can be very useful, especially if we have a lot of commands. So please use it as often as you can, because the result will be much user-friendly than without comments or description. The last thing we have to do is actually delete these two lines, because it doesn't useful anymore. Then use the servo write function, because we made sure that it works like it has to. So upload this sketch, and if everything went good, it should move the servo. So let's try it out. As we can see, if we specify a number here in a valid range, the servo will move exactly to the degree which we typed in as an argument. Of course, we can try without parameters or with wrong parameters. It won't do anything wrong. Also, we can try an invalid number. It won't crack or anything, just works like intended. Let's create some useful commands to see what can we also do with the terminal interface. The LED state command will print out the state of the LED. It's basically a simple query to check the state of the output pin which goes to the LED. The get servo command is basically the same, but with the servo. It can print out the position of the servo. Then lastly, the reboot function can be a very useful function, especially if something went wrong with our logic and the device needs to reboot itself without user interaction. So I think it's one of the most important functions in an advanced system like a robot or a network device. Also, we have to create the callback functions for our commands. The LED state function will print out the state of the GPIO pin which is connected to the LED. It's basically just a printing function. The get servo function is similar, it just prints out the position of the servo. There's a function for this in the ASP32 servo library, so you can use it here. The reboot function also very simple. It's just printing out the rebooting state. It waits 2 seconds, then restarts the device. ESP boards usually have a function for this in the API called esp.restart. If you have an AVR board, you can trick it with the watchdog. Set some really short time for the watchdog and let it reboot the microcontroller itself. If we press the LED state, it should work. Yes, it works fine. Then we have the set servo command. It looks like it's working. Also, it gets the position from the servo. Then lastly, we try to reboot the board. Yeah, it works fine. So the next feature can be very useful if you create robots. If you prototype a robot and something went wrong, you have to stop the robot as fast as you can. So the standard terminal interfaces usually have an abort function dedicated to the Ctrl+C key. So if you press Ctrl+C in a standard terminal, like the Linux terminal or PowerShell, it will abort the running process. So in Shellminator, there's a way to override the key behavior of the Ctrl+C key. By default, if you press the Ctrl+C key, it deletes whatever you printed or typed into the terminal and start a new session for it. But if you want to do some logic attached to this key, you can override it. To do that, we have to create a function. Let's call it abort handler, and we have to tell Shellminator to use this function every time you press the Ctrl+C key. There's a function for that called override abort key, and you have to pass the function as an argument, which have to be called every time you press the abort key. Now we have to create the function itself. Let's just print out that the abort key is pressed to see how it works. So if we press the Ctrl+C key, now we can see that it calls the abort handler function and prints out the message abort key pressed. So to make it actually useful in our application, let's say that we have a very critical valve connected to the shaft of the servo and it has to be centered if something went wrong. Then also we have to turn off the LED to indicate that it's not working correctly. So the behavior of our abort handler will be setting the servo to the center position and turning off our LED. It's a good practice to make the actions happening first, then printing out some useful information, because if it's a critical thing, we have to do the necessary steps before anything which is not so critical, like printing out that the abort key is pressed or some critical informations. So let's try it out. Set the servo to some position, then turn on the LED. Then we have to press the abort key to try it out. So it looks like it's working again. So then press Ctrl+C and the abort function is called. The abort handler will start the abort procedure and we can safely shut down our robot without any damage. We successfully overloaded the abort key behavior in Shellminator, but also we can override the behavior of the arrow keys. It can be very useful if you have some motors and you want to do some jogging with them. It is very intuitive, so we can do that also. So let's create two functions called jogging on and jogging off. Jogging on will override the key behavior for the up and down arrow keys. Jogging off will turn it back to the normal state, which is the command history in Shellminator. So let's create the prototypes as well for this function. So let's create the logic for this as well. So just like in the init section, we have to override the key behavior with the override up arrow and override down arrow functions for the jogging on command, and for the jogging off command we have to free up the behavior. So there's a free up arrow and free down arrow commands for this. So we have to create two functions called jogging up event and jogging down event. These functions will be called every time you press the up or down key with the overridden behavior. We have to create the prototypes first, and we have to implement some logic. So it actually just reads the actual position of the servo, add or subtract some stepping value to it, checks the boundaries, then write the new value to the servo. Let's try it out. So if we enable the jogging, then we press the up or down keys in the terminal, it will jog our servo like it has to. If we have to turn off this behavior, we have to turn off the jogging, then it will be back to normal, which is command history. It is a very nice feature to test some servo movement, to move some axis in your robot. If you have to, you can make a car, a remote controlled car with it, and control it with the arrow keys in the keyboard. So it is very useful. So the next thing is to personalize the terminal interface a bit. If you go to the documentation of Shellminator, you can see that there's a function called attach logo. In the documentation there's a link to create some ASCII art like Arduino or anything else, and you can choose from a really good variety of fonts. Just play with it a bit. So press select and copy, then open the other link in the documentation. It will create a C-like text string from the typed text above. Then we can create a string that contains this data. Also, we have to delete this last line, it's not useful. Then we have to pass this logo to Shellminator object itself. There's a function called attach logo, so we will use that in the init section. And if we upload this sketch, we should see that it's printing out our logo after the boot section. So after we open the terminal, we see this garbage looking thing. The reason is because it just printed \n characters, which is new line, but we need carriage return as well, so we have to modify the logo string a bit to make it work. So let's do that. So basically we just have to modify the ending to make it \r\n instead of the regular \n, and now it should work. So as we can see, it looks much better and much professional now, and it also works like before. The next part of the tutorial will be showing you how to use it with the Wi-Fi client library as well. So if you have a wired device, the serial implementation which we have done already is enough usually. But if you want to make a robot which is remote controlled, or device which is network enabled like the ESP32, ESP8266, it is a good practice to make it work with TCP as well. So in order to create a TCP socket to your terminal interface, it is very simple. Every overloading is handled by Shellminator and Commander internally. You just have to create a web server object, initialize it, then pass it through Shellminator and Commander as well. So I will show you how to do that in a second. Firstly, we have to include the necessary header files in our project to make the Wi-Fi library work. Then we have to create two variables to store our Wi-Fi SSID and Wi-Fi password. You have to fill it with your local settings. We have to create a server object, a client object, and we have to create another Shellminator object for the Wi-Fi shell. It's also a good practice to create as much Shellminator objects, as much channels you have. For example, in this tutorial we have a channel for the serial port, and we have a channel for a TCP client. Okay, so in the init section we have to initialize the other terminal interface as well. Then we have to initialize our Wi-Fi peripheral, which is very simple. After the initialization, it is also a good practice to print out some network information. This way will be easier to connect to our TCP socket. Lastly, we have to add it to the loop as well. So basically we will search for available clients in our TCP socket. If we have one, we initialize the shell. It is required because every time you open a TCP socket to your terminal client, it will print the logo. It's a good indicator that you open the good socket port. Then while we are connected, we update the terminal as well. In the ESP ecosystem, it is required to give some delay after a while loop because it's a multitask system, and the other tasks need some time to do their job. Usually 5 millisecond delay is enough. So let's try it out. Sorry, one mistake, the server port did not define, so we have to define it at the beginning of our code. So let's check it out. So if we open the terminal in PuTTY just like before, it should connect. Yeah, it's working, but it has some problems in the formatting. We have to add another print OK. My mistake, sorry. Now it looks much better. So it connected to my Wi-Fi network with this IP and this port. So if we open PuTTY again, if we change the settings in PuTTY to row instead of serial, then type the IP address and the port, it should work. It's also a good practice to save this for future use. Save, then open it. So as we can see, now we have a working terminal over TCP, and it's kind of junky. This is because we have to configure something else also in PuTTY to make it work. We have to go to change settings, terminal, then we have to disable the local echo and local line editing. It can be automated. So now it works just like with the serial port. Also, all of the functions are available, so we can use it as well. So if we have a wireless robot, it can be also used with Wi-Fi. There's only one problem with this implementation. As we can see, the Wi-Fi terminal works, but if we want to try the serial terminal, it now hangs. Why is that? So if we scroll up to the loop function, we can see that there's a while loop inside it. As long as we have a TCP socket open, it won't reach the other update function. As soon as we exit from the TCP socket, it works like fine. If it's not acceptable in your design, I will show a trick how to use it parallel if you want. So in the ESP8266 or the ESP32 ecosystem, the core library is built upon the FreeRTOS system. FreeRTOS is a minimalistic kernel which allows you to do some threading, multi-threading in your applications. So it's a good practice to take the Wi-Fi section to the parallel loop in our project. So we have to make a task for that. Let's just call this to terminal client task. Then at the end of our initialization section, we have to start this task. We have to remove everything from the loop which is related to the Wi-Fi stuff. Now it's just the serial shell. Then create the task logic itself. Basically, it's a parallel loop function, and its job is to handle the Wi-Fi shell stuff. So let's try it out. If we open the two terminals like before, it should work. Now I made a mistake. My ESP board always reboots when I open a COM port, so I have to reopen the socket one because the reboot event killed it. So yeah, we have to change settings, disable the echo. Now it works, and now the serial terminal works as well. So they run at the same time. Let's create a small command which prints out some diagnostics about our network. Firstly, we have to create the data in our API tree. We have to create the prototype function. Then we have to create the actual logic to this command. Okay, so it basically just prints out the RSSI of our network, the IP address, the local IP address, and the port. So as we can see, the command works and it prints out the relevant information about our network. There are some special use cases when you need to monitor something frequently and automatically. So in the next section I will show you how to create a command which prints out the nearby stations frequently. Let's create a command called Wi-Fi scanner. Create a prototype function for it. Then implement the actual logic for this function. So it basically uses the API from the ESP library to scan the networks and prints out each of them in a formatted way. As we can see, it works, but it has some problems. For example, if it starts to repeat automatically, it prints the whole thing again after the previous one, so it's not very readable. The abort mechanism works well, I think. If you press any key in the terminal, it will abort the next section. Okay. So let's modify the code a bit. The modified version has some extra terminal features at the end. So basically at the beginning of the loop, we print out all of the available networks. And at the end, we clear as much line as we printed before. In this way, we have a list which is consistently placed in a fixed position in our terminal. So if you try it, you will see what I mean. So if we try now, it looks much more present than before, and every time it reprints the values, it actually clears the previous data, so it's always in a fixed place in the terminal. It looks much better. Also, if you press a key, any key, it will stop the scanning and you can use the terminal as intended. So thank you guys very much for watching my video. I really appreciate it, and I hope you can use Shellminator and Commander-API for your robot projects. The library itself is platform IO compatible, and you can use it with any AVR boards or the ESP32 or ESP8266 ecosystem. I hope you can build awesome projects with it, and please share your work with the world if you do. Thank you for watching.